Good evening and welcome to Dreamy Academy. Tonight we embark on a journey so vast, so ancient, that it stretches the very fabric of imagination. As we begin, I'd love to know where you're watching from, your city, your country, perhaps even what the night sky looks like outside your window. If you enjoy these peaceful explorations of science, please take a moment to like the video and subscribe. It truly helps this little corner of quiet curiosity grow. To those already subscribed, thank you sincerely for being part of this slow and thoughtful adventure. And if you'd like to be gently reminded when our next journey begins, the notification bell is there for you. Tonight, we will attempt to hold the entirety of time in our minds, to trace the universe from its very first breath, a breath that wasn't an explosion into space, but the quiet, relentless blossoming of space itself. Imagine, if you will, that the very air you breathe, the atoms in your hand, the light that guides your gaze are all fragments of an ancient story, whispers from an origin almost beyond comprehension. We speak of scales so immense that 1,000,000 years feels like a fleeting moment, and distances so vast that light, travelling at its impossible speed, takes billions of years to reach us. Yet, within this immensity there is an intimate connection. The carbon in your bones, the iron in your blood, these are not merely elements. They are ancient travellers, forged in the hearts of distant stars, scattered across the cosmos and gathered here, within you. This is not poetry alone, it is physics. It is the deep, resonant truth of our existence. To contemplate cosmology is to contemplate ourselves, not as separate observers, but as integral threads in the grand tapestry of everything. It is a journey that rewards patience, a story that unfolds like the slow turning of geological strata, each layer revealing a deeper truth, each concept a new facet of a universe that is both profoundly complex and exquisitely beautiful. Let us drift together into this gentle understanding, allowing the sheer depth of it to lull us into a peaceful contemplation of the greatest story ever told. What is time, really, when you try to hold it in your mind? Is it a river flowing inevitably forward, or a vast ocean in which all moments exist, waiting to be perceived? To begin our journey into cosmology, we must first learn to stretch our understanding of time until it becomes almost elastic, capable of encompassing not just human lifetimes, or even the slow dance of continents, but the entire lifespan of the universe itself. Picture, if you will, the quiet moment before anything we know existed. Not darkness, for there was no light, not emptiness, for there was no space, just a profound, unimaginable potential waiting to unfurl. This is where our story truly begins, at the threshold of existence, where the very concept of before loses its meaning. Roughly 13.8 billion years ago, the universe as we know it began. We call this beginning the Big Bang, a name that, while vivid, is perhaps a little misleading. It wasn't an explosion into an empty void because there was no void for it to explode into. Instead, it was the rapid, accelerating expansion of space itself, carrying everything within it. Imagine baking a loaf of raisin bread. As the dough rises, the raisins move further apart from each other, not because they are flying through the dough, but because the dough itself is expanding. In a similar, deeply counterintuitive way, the early universe was incredibly dense and impossibly hot, a swirling, energetic plasma where the very distinction between matter and energy blurred. In those first fleeting fractions of a second, a trillionth of a trillionth of a trillionth of a second, the universe expanded at an astonishing rate, far faster than light could travel. This period, known as inflation, smoothed out the cosmos to an almost unimaginable uniformity. Yet, not perfectly uniform. At these infinitesimal scales, the universe operates by the rules of quantum mechanics, where certainty gives way to probability, and even quote-2 space is alive with fleeting energies. These quantum fluctuations, tiny ripples in the fabric of the nascent universe, created regions ever so slightly denser and ever so slightly less dense than their surroundings. These minuscule variations, smaller than an atom, were the most subtle of seeds, planted in the earliest moments, destined to grow into the grand structures we observe today. As space continued to expand, it also cooled. Imagine a gas expanding rapidly. It loses heat. The early universe was no different. Within the first few minutes, the temperature dropped enough for the fundamental particles we know, quarks and electrons, to coalesce. Quarks then bound together to form protons and neutrons, the building blocks of atomic nuclei. This was a critical moment. The universe was still too hot for stable atoms to form, but it was cool enough for the first, lightest nuclei to be forged. Through a process called Big Bang nucleosynthesis, protons and neutrons fused together to create hydrogen, helium, and tiny traces of lithium. These three elements were, for a time, almost the entire chemical inventory of the cosmos. Every other element, the carbon in a redwood, the oxygen in your breath, the iron in your blood, did not yet exist. For the next 380,000 years, the universe remained a superheated, opaque fog. Electrons were not yet bound to nuclei. They were free, zipping around, constantly scattering photons of light. It was like being inside a star, where light cannot travel far before being absorbed and re-emitted. The cosmos was a plasma, a vast, glowing, utterly impenetrable soup. This was the quote 3 in a very literal sense, not because there were no photons, but because those photons were trapped, unable to travel freely and illuminate the emerging universe. But the expansion continued, patiently, relentlessly, and with it, the cooling. Finally, a moment arrived, about 380,000 years after the Big Bang, when the temperature dipped below a critical threshold, around 3000 Kelvin. At this point, the free electrons, which had been too energetic to settle, could at last combine with the hydrogen and helium nuclei. They formed the first stable, neutral atoms. This event, known as recombination, though it was the first time these particles combined, was profound. Suddenly, with the electrons bound within atoms, the universe became transparent. The photons, previously scattered and trapped, were now free to travel unimpeded through space. This sudden release of light is perhaps one of the most beautiful and tangible echoes of creation we can detect. These photons, having travelled across the entire history of the universe, reach us today, stretched and cooled by billions of years of cosmic expansion. What began as a searing glow hotter than the surface of the sun has now cooled to a faint microwave background radiation, just 2.7 degrees above absolute zero. This is the cosmic microwave background, or CMB, a uniform hum of energy filling all of space, a gentle whisper from the birth of everything. It's like an ancient photograph of the universe when it was just an infant, still almost perfectly smooth, but with those subtle, essential ripples. And it is those ripples, those tiny quantum fluctuations from the very first moments, amplified by the expansion of space and the patient, relentless pull of gravity, that began to sculpt the universe we see. Over millions upon millions of years, the slightly denser regions slowly, imperceptibly, began to gather more matter. Gravity, an incredibly weak force on human scales, is utterly dominant on cosmic scales. It pulls gently but universally, drawing matter together, building up structure from the nearly featureless early cosmos. The universe, it seems, has a profound tendency towards organization, given enough time and the right initial conditions. So, we have a universe that began incredibly hot and dense, expanded rapidly, cooled, and formed the simplest atoms, releasing a flood of light that we can still detect. And within that primordial light, we see the faint imprints of quantum fluctuations, the initial whispers of complexity. What does this tell us? It tells us that the universe is not static, not an eternal, unchanging stage, but a dynamic, evolving entity with a definite beginning and a story that continues to unfold. There's a particular comfort in understanding that the vastness around us emerged from such humble, almost imperceptible beginnings. The very act of perceiving the CMB, of listening to that ancient hum, connects us directly to the moment when the universe first became transparent. It is a profound reminder that we are not separate from this grand narrative, but an integral part of it. The laws of physics that governed those first moments, the expansion of space, the cooling of energy, the formation of particles, are the same laws that operate in your own body, in the stars above, and in the distant galaxies. This initial simplicity, dominated by hydrogen and helium, sets the stage for everything that follows. Without these first, lightest elements, without the patient cooling and the initial seeds of density, the universe would have remained a uniform, featureless expanse. But because of these elegant, fundamental processes, the universe began its slow, deliberate journey toward complexity. We are witnessing, through scientific observation, the very genesis of structure, the initial stirrings of the cosmic architecture. The universe, in its earliest infancy, was a canvas of almost pure potential, waiting for gravity to begin its slow, magnificent work of painting in the stars and galaxies. We've journeyed through the universe's first breath, witnessing the birth of space and time, the forging of the lightest elements, and the release of that ancient light that still bathes us. We've seen how tiny quantum ripples became the blueprint for everything, but a universe composed almost entirely of hydrogen and helium, however grand, cannot create the intricate forms of life, this solid ground beneath our feet, or the vibrant colours of a sunset. Where, then, did all the other elements come from? The carbon, the oxygen, the nitrogen, the iron, the very stuff of us. How did these fundamental seeds of structure grow into the luminous islands of stars and galaxies? That question, of how the universe built its more complex ingredients, leads us from the grand expansion to the intimate, fiery hearts of the first stars, where the true alchemy of creation began. Welcome back, dear friends, to our shared journey through the cosmos, here at the Dreamy Academy. In our last gathering, we witnessed the universe's first breath, its astonishing expansion, and the crucial moment when light was finally set free, painting the cosmic microwave background across the heavens. We left our universe approximately 380,000 years old, a vast, transparent ocean of hydrogen and helium, gently rippled by the faint echoes of inflation. But if you recall, a profound question lingered. Where did the heavier elements, the carbon, the oxygen, the iron, the very building blocks of life as we know it, come from? The early universe in its infancy was a remarkably simple place, primarily composed of the lightest elements. The stage was set, the curtain lifted, but the cast of characters was still quite small. Imagine, if you will, this primordial cosmos, a serene, almost featureless expanse still profoundly dark. Though light could now travel freely, there were no sources of light, no stars, no galaxies to illuminate the grand theatre. This was the era aptly named the Cosmic Dark Ages. For millions upon millions of years, the universe drifted, cooling steadily, a vast quiet canvas awaiting its first strokes of brilliance. Yet within this stillness, gravity, the universe's patient sculptor, was tirelessly at work. Those infinitesimal ripples in the cosmic microwave background, those subtle variations in density that were imprinted during inflation, were not merely decorative. They were blueprints, gravitational whispers across the void. In regions where matter was ever so slightly denser, gravity began its slow, relentless pull, drawing in more hydrogen and helium gas from the surrounding emptiness. Think of it as a cosmic gathering. Over immense spans of time, hundreds of millions of years, these denser pockets grew like invisible eddies in a cosmic current. The gas within them became hotter, denser, spiraling inward, collapsing under its own immense weight. It was a slow, majestic dance of compression, each atom drawn inexorably towards its neighbours. And then a moment arrived that changed everything. In the deepest, most compressed cores of these collapsing gas clouds, the pressure and temperature reached an unimaginable threshold. The hydrogen atoms, squeezed together with such ferocity, began to fuse. Not just one or two, but billions upon billions of them, igniting in a spectacular, self-sustaining thermonuclear reaction. This, my friends, was the birth of the first stars. We call these ancient celestial giants population 3 stars, and they were truly magnificent. Unlike the stars we see today, born from gas clouds already enriched with heavier elements, these pioneers were pristine, forged solely from the universe's original hydrogen and helium. They were colossal, hundreds, perhaps even thousands, of times more massive than our own sun, and burned with an intensity almost beyond comprehension. Their lives, though glorious, were tragically brief, lasting only a few million years, a mere blink in cosmic time. But oh, what a legacy they left! Within the fiery crucibles of their cores, the universe's grand alchemy truly began. As hydrogen fused into helium, the immense gravitational pressure continued to squeeze, pushing the boundaries of creation. Helium atoms in turn fused to form carbon. Carbon then fused with more helium to create oxygen, and so it continued, step by painstaking step, through a process we call stellar nucleosynthesis. Imagine the heart of such a star, a colossal, living furnace where the fundamental forces of nature conspire to build new matter. Here, in this cosmic forge, the elements up to iron were painstakingly crafted. Each new element, a testament to the star's immense power and the relentless march of nuclear fusion. Silicon, sulfur, magnesium, all born from the primal hydrogen and helium, nurtured in the incandescent belly of a star. Yet, as we mentioned, these first stars were fleeting. Their colossal mass meant they consumed their nuclear fuel at an astonishing rate. Once their core was largely converted to iron, a crucial turning point, as fusing iron actually absorbs energy rather than releasing it. The delicate balance between outward thermal pressure and inward gravitational collapse was shattered. What followed was a cataclysm of unimaginable proportions, a supernova. In a fraction of a second, the star's core imploded, compressing to an incredible density, only to rebound with an explosive force that ripped the star apart. For a brief, glorious moment, a single supernova could outshine an entire galaxy, and in that violent incandescent instant, something truly extraordinary occurred. The immense energy released during the collapse and rebound was so profound that it briefly overcame the energy barrier for fusing iron. In that fleeting, violent flash, elements heavier than iron, the gold in your rings, the silver in your heirlooms, the uranium that powers our deepest technologies were forged. These supernovae were not just spectacular death throes. They were the universe's ultimate dispersal mechanisms. They scattered the newly synthesized elements, the carbon, oxygen, nitrogen, iron, and all the heavier elements across vast stretches of the nascent cosmos. Imagine a cosmic gardener sowing seeds of creation across the fields of space. These heavy elements, born in fire, were now adrift, enriching the pristine hydrogen and helium gas clouds that permeated the universe. And this, my friends, brings us to the next chapter in our cosmic narrative, the formation of later generations of stars and eventually galaxies. The gas clouds, now subtly laced with these metal elements, as astronomers call anything heavier than hydrogen and helium, began their gravitational dance anew. But this time, the presence of these heavier elements made a crucial difference. They allowed the gas to cool more efficiently, facilitating faster and more complex gravitational collapses. From these enriched clouds, new stars were born. Stars like our Sun, which contains a healthy complement of heavier elements, including enough carbon to form life, enough oxygen to breathe, and enough iron to course through our veins. These second and third generation stars were often born in vast stellar nurseries, coalescing into the magnificent structures we call galaxies. The very first galaxies were likely smaller, irregular aggregations, but over billions of years they merged, grew, and sculpted themselves into the spirals and ellipticals we observe today. So, when you gaze up at the night sky, understand that every star you see, every glimmering galaxy, is a testament to this grand, patient, relentless process of cosmic evolution. The elements that make up your hand, the air you breathe, the very planet beneath your feet, all were forged in the hearts of long-dead stars, scattered across the cosmos by their explosive demise, and then patiently reassembled by gravity into planets, moons, and ultimately us. We are, quite literally, stardust made conscious, capable of contemplating our own incredible origins. This intimate connection, this profound realization that we are integral threads in the grand tapestry of everything, is perhaps the most awe-inspiring truth cosmology offers. You're not separate from the cosmos. You're a vital, breathing part of it. The alchemy of creation, begun in the Big Bang and continued in the hearts of stars, flows through you. Yet even with this grand story unfolding, the birth of elements, the formation of stars and galaxies, we are only beginning to scratch the surface. As these vast structures began to form and evolve, astronomers observed that something was amiss. The visible matter, the stars, the gas, the dust, simply didn't have enough gravitational pull to hold galaxies together or to explain their observed rotation speeds. It was as if there were unseen architects at play, influencing the cosmic dance without revealing themselves directly. And so, we arrive at one of the universe's most profound and enduring mysteries, a puzzle that continues to challenge our understanding of reality, the existence of what we call dark matter and dark energy. These enigmatic components, though invisible and undetectable by conventional means, exert a powerful influence over the structure and fate of our universe. They are the silent partners in this cosmic ballet, pulling strings from behind the scenes. We will, in our next session, attempt to peel back the layers of this profound enigma to understand how these unseen forces shape the very fabric of our reality. For now, take a moment to absorb the incredible journey we've undertaken, from a universe of pure energy and light to one populated by the heaviest elements, crafted in stellar furnaces and scattered to form new worlds. Thank you for sharing this quiet, thoughtful adventure with me. Your curiosity, your willingness to imagine the unimaginable is what makes this exploration truly special. Until we meet again, may your mind continue to wander among the stars. Welcome back, dear friends, to our shared journey through the cosmos, our quiet, relentless blossoming of understanding. We left off at a precipice, didn't we? A moment where our carefully constructed narrative of the universe, a story of stardust and light, encountered profound shadows. We spoke of the elements that forge us, the stars that birthed them, and the vast, empty stretches that hold them. But then, we hinted at the unseen, the unspoken, the profound mysteries that make up the vast majority of our universe. Dark matter and dark energy. It is here, in the realm of the invisible, that the universe truly stretches the very fabric of our imagination, inviting us to look beyond what our eyes can see, or even what our most powerful telescopes can detect. We are not just exploring the known, we are peering into the profound unknowns, the cosmic enigmas that whisper of a universe far grander and far more peculiar than we might have ever conceived. Let us begin with dark matter, a silent architect, a gravitational ghost that, while unseen, exerts an undeniable influence on the tapestry of the cosmos. Imagine, if you will, a grand cosmic ballet, where galaxies spin and whirl in elegant formation. For decades, astronomers observed these celestial dancers, measuring their rotational speeds. What they found was puzzling, even contradictory to our understanding of gravity. The stars at the outer edges of galaxies we expected should be moving slower, just as planets further from the sun orbit more slowly. But instead, they moved with astonishing speed, as if held by an immense invisible hand. This observation, like a cosmic whisper, first truly solidified with the groundbreaking work of Vera Rubin and her colleagues in the 1970s. They meticulously mapped the rotation curves of numerous galaxies and consistently found that the visible matter, the stars, gas, and dust, simply wasn't enough to generate the gravitational pull needed to keep those rapidly spinning outer stars from flying off into intergalactic space. There had to be something else, an enormous halo of unseen mass enveloping each galaxy, extending far beyond its luminous boundaries. This something else we now call dark matter. It does not interact with light in any way we understand. It does not emit, absorb, or reflect photons. It is utterly transparent, a phantom presence that passes through us, through our planet, through the stars themselves, leaving no trace, save for its gravitational embrace. We cannot see it, but we can feel its pull. It acts as the gravitational scaffolding upon which the visible universe is built. Without this invisible scaffolding, galaxies would simply tear themselves apart. Consider the phenomenon of gravitational lensing. Just as a heavy glass lens bends light, immense concentrations of mass in the universe can bend the light from distant galaxies, distorting their images into arcs and rings. When we observe these lensing effects, particularly in massive galaxy clusters, the amount of visible matter present is often insufficient to explain the degree of bending we see. Again, the invisible hand of dark matter must be at play, providing the additional mass needed to warp spacetime and create these cosmic mirages. So, what is dark matter? It is not ordinary matter, the baryonic matter that makes up everything we can touch and see. The protons, neutrons, and electrons. We know this from various lines of evidence, including the abundances of light elements forged during Big Bang nucleosynthesis. If dark matter were baryonic, it would significantly alter those primordial ratios. Nor is it simply a collection of faint dark objects like black holes or brown dwarfs. While these exist, they don't account for the sheer quantity of dark matter required. Instead, we hypothesize that dark matter is composed of entirely new, exotic particles. Particles that interact with normal matter only through gravity and perhaps through the weak nuclear force. Scientists are tirelessly searching for these elusive particles in underground laboratories, hoping to detect the faintest tremor of their passage. It is a profound quest, a testament to our insatiable curiosity, to understand the true nature of this invisible force that constitutes roughly 27% of the entire universe's mass energy budget. Without dark matter, the cosmic web, the vast network of filaments and voids that structures the universe, would not have formed as we observe it. It was dark matter that provided the initial gravitational seeds, amplifying those tiny quantum fluctuations we discussed in Chapter 1, allowing matter to clump together and eventually give birth to galaxies and galaxy clusters. Now, let us turn our gaze to an even more profound mystery, one that governs the ultimate fate of everything: dark energy. If dark matter is the unseen hand that holds galaxies together, dark energy is the invisible force that pushes them apart, accelerating the expansion of the universe itself. For much of the 20th century, we understood that the universe was expanding, a grand cosmic inflation set in motion by the Big Bang. Gravity, we assumed, would be working to slow this expansion down, perhaps even eventually reversing it into a big crunch. But then, in the late 1990s, a startling discovery emerged from observations of distant type-wire supernovae, specific types of exploding stars that act as standard candles for measuring cosmic distances. These supernovae appeared dimmer than they should have been for their measured redshifts, implying that they were further away than predicted. The only way for them to be further away was if the expansion of the universe had not been slowing down, but rather speeding up. This revelation sent shockwaves through the scientific community. It meant that something was actively working against gravity, pushing the fabric of space-time apart at an ever-increasing rate. This mysterious repulsive force permeating all of space is what we call dark energy. It is not localized like matter, it is intrinsic to space itself. As space expands, more space is created, and with it, more dark energy, leading to a self-perpetuating acceleration. What is dark energy? This, dear friends, is arguably the greatest unsolved mystery in all of cosmology. Some theories suggest it is a cosmological constant, a fundamental property of empty space, an inherent energy density of the vacuum itself. Others propose it might be a dynamic field changing over time, a concept known as quintessence. We do not yet know, but we do know its profound influence. It accounts for approximately 68% of the total mass energy of the universe. Think about that for a moment. The matter we understand, the atom that form us, the stars, the planets, the galaxies, all of this visible, tangible reality makes up only about 5% of the universe. Dark matter, the invisible gravitational glue, constitutes another 27%, and the vast, overwhelming majority, nearly 70%, is this enigmatic dark energy, silently, relentlessly driving the universe towards an unknown future. We are, in essence, living in a universe dominated by forces we barely comprehend. This realization, far from diminishing our wonder, amplifies it. It highlights the humility required in our scientific endeavors, reminding us how much there is yet to discover, how much more subtle and intricate the universe truly is. Within this dance of known and unknown, this interplay of visible matter, dark matter, and dark energy, the cosmic web has continued to evolve. Dark matter halos, those invisible gravitational anchors, became the cradles for galaxy formation. Gas, enriched by the supernovae of the first stars, began to cool and collapse within these halos, forming the majestic spirals and stately ellipticals we see today. Gravity, patiently and relentlessly, pulled these nascent galaxies together into clusters, and clusters into superclusters, interconnected by vast filaments of dark matter and gas, separated by immense, nearly empty voids. This is the large-scale structure of the universe, a grand, frothy network shaped by the interplay of gravity and the unseen. Galaxies themselves are not static entities. They are dynamic, evolving systems, constantly interacting. Mergers between galaxies are common, spectacular events that reshape their structures, ignite bursts of star formation, and often feed the supermassive black holes lurking at their centers. These colossal black holes, millions or even billions of times the mass of our Sun, are now understood to co-evolve with their host galaxies, playing a crucial role in regulating star formation and galaxy growth. From the initial quantum fluctuations to the formation of stars, then galaxies, and now the complex interactions between them, it is a continuous unfolding narrative, a grand, intricate ballet choreographed by gravity and the mysterious dark components. As dark energy continues its relentless work, the universe's expansion accelerates. Galaxies that are not gravitationally bound to our local group are receding from us at ever-increasing speeds. In the unimaginably distant future, our observable universe may become a lonely island, surrounded by an ocean of darkness, with all other galaxies having receded beyond the reach of our light. The cosmic story, however, does not end there. It is a story of continuous transformation, of new questions arising as old ones are answered. We stand at a unique moment in cosmic history, able to observe the remnants of the Big Bang, the distribution of dark matter, and the accelerating expansion driven by dark energy. We are privileged witnesses to a universe that is both profoundly beautiful and deeply mysterious. The quest to understand dark matter and dark energy is not just a scientific pursuit. It is a philosophical journey, a profound inquiry into the fundamental nature of existence itself. It reminds us that our story, the story of humanity, is inextricably woven into this grand, unfolding narrative of everything, a narrative still being written, with vast, wondrous chapters yet to be revealed. Thank you for joining me on this exploration of the known and the gloriously unknown. We concluded our last shared moment peering into the profound mystery of dark matter and dark energy, those silent, unseen architects of the cosmos. We grappled with the startling revelation that the universe, far from slowing its expansion, is actively accelerating, driven by a force so pervasive, so fundamental, yet so utterly enigmatic, that it challenges the very limits of our comprehension. It's a universe largely defined by what we cannot see, what we do not fully understand, a grand tapestry woven with threads of the known and vast swathes of the unknown. Today, we journey further into the implications of this accelerating expansion, inviting you to contemplate not just the universe's past and present, but its potential, distant future. What does it mean for the grand narrative that the very fabric of space is stretching patiently, relentlessly at an ever-increasing pace? Imagine, if you will, the universe as a vast, endlessly expanding ocean. For a long time, we thought the waves might eventually calm or even recede, but now we observe them growing stronger, pushing the distant shores further and faster away from us. This acceleration has a profound consequence for what we can perceive, for what remains connected to our observable cosmic island. As space stretches, the light from distant galaxies is stretched with it, reddening, fading, eventually becoming so attenuated that it will effectively vanish from our sight. Galaxies that are currently within our cosmic horizons, brilliant beacons in the night, will, in the unimaginably distant future, recede beyond a point of no return. Their light will simply never reach us, no matter how long we wait. It's as if they are slipping behind an ever-approaching silent veil, leaving us in a progressively emptier, lonelier cosmic neighborhood. This isn't a physical journey away from us in the traditional sense, but rather the expansion of the space between us and them. It's like watching ships sail away on that endless ocean. Eventually, they dip below the horizon, not because they've ceased to exist, but because the curvature of the Earth, or in our cosmic analogy, the curvature and expansion of space, prevents their light from reaching our eyes. But in this cosmic scenario, the horizon itself is moving, shrinking, swallowing more and more of the distant lights. Consider the profound implications of this. Future civilizations, countless eons from now, if humanity or any other intelligent life persists, might look up at a night sky that is profoundly different from ours. They might see only their local group of galaxies, bound together by gravity, an isolated island in an ocean of darkness. The grand, sweeping cosmic web, the countless galaxies that currently pepper our telescopes, might simply be gone from view, their light stretched into oblivion. They might never know the true scale and richness of the universe we are privileged to observe today, an intimate connection to billions of years of cosmic history revealed in every photon. This accelerating expansion leads us to what cosmologists currently consider the most probable ultimate fate of our universe, the Big Freeze, or heat death. It's not an explosion or a dramatic collapse, but a gradual, inexorable fading into cold, dark emptiness. Let us trace this chilling yet strangely serene trajectory. In the far, far future, long after our sun has exhausted its fuel and become a white dwarf, and even after these stellar remnants have cooled into black dwarfs, the universe will continue its relentless expansion. Galaxies not gravitationally bound to our local group will have receded beyond our observable horizon, leaving only a vast, empty void between our galactic island and the next. Stars, the cosmic furnaces that forge elements and bring light, will eventually burn out. New stars will cease to form as the gas and dust required for their birth become too sparse, too cold, too spread out across an ever-expanding canvas. The last embers of stellar life will flicker and die. What will remain are stellar corpses, white dwarfs, neutron stars, and the ultimate gravitational behemoths, black holes, and even these titans will not endure forever. Black holes, through a process known as Hawking radiation, are theorized to slowly, agonizingly slowly, evaporate over truly astronomical timescales so vast they make the age of the universe thus far seem like a fleeting blink. Imagine black holes the size of galaxies, patiently radiating away their mass, particle by particle, over 100 billion years or more, a number so large it loses all human meaning. Eventually, even the last black hole will have evaporated, leaving behind a universe populated by an incredibly dilute soup of fundamental particles, photons, neutrinos, electrons, positrons, all separated by immense incomprehensible distances. The very concept of temperature will lose meaning as there will be no energy gradients left to drive any process. All available energy will have been spread out to its maximum possible extent, reaching a state of maximum entropy. This is the essence of the Big Freeze, a universe that has run out of steam, where all activity has ceased, where every particle is isolated, where there is no heat, no light, no motion, no change. A universe that is infinitely cold, infinitely dark, and infinitely empty. It's a quiet, relentless blossoming of space itself, leading to an ultimate stillness. We have, of course, considered other potential fates throughout the history of cosmology. There was the Big Crunch, where gravity would eventually overcome expansion, pulling everything back together into an incredibly dense hot singularity, a reverse Big Bang. There was also the terrifying Big Rip, a more violent scenario where dark energy would grow so strong that it would eventually tear apart galaxies, then stars, then planets, then atoms themselves, leaving nothing but fundamental particles scattered across an infinitely expanding void. But current observations, particularly of the universe's accelerating expansion, strongly favour the Big Freeze. The universe appears to be heading towards a state of eternal cold dispersal. This journey into the distant future can feel daunting, even melancholic. To contemplate such an ending so vast and indifferent can make our brief lives, our striving for understanding, seem infinitesimally small. Yet, it is precisely in this contemplation that we find a unique and profound beauty. We are here now in this precious sliver of cosmic time, capable of observing, theorizing, and even glimpsing these unfathomable futures. We are the universe's way of reflecting upon itself, of telling its own story. We hold within us the echoes of those first stars, the elements forged in their fiery hearts, the cosmic dust that coalesced to form our world, and the very consciousness that allows us to ask these grand questions. Our ability to piece together this cosmic narrative, from the quantum fluctuations of the very beginning to the potential cold silence of the far future, is a testament to the power of human curiosity and intellect. We are not just passive observers, we are integral threads in this grand tapestry, connected to every photon, every atom, every gravitational wave that has ever been. The beauty of our present moment lies in the fact that the universe is still rich, vibrant and teeming with wonder. The night sky still sparkles with billions of galaxies, each a realm of untold stars and possibilities. The cosmic microwave background still whispers its ancient tale across the heavens. Dark matter still sculpts the invisible scaffolding, and dark energy still pushes the boundaries of our understanding. This is our time. This is your time. To witness, to learn, to marvel, to embrace the mystery and the grandeur of it all, not as something distant and separate, but as an intimate part of your own existence. The universe, in all its vastness and complexity, is unfolding around us and through us right now. As we conclude this chapter, let us hold on to this thought. Even as we peer into the potentially empty future, we are grounded in a present moment overflowing with discovery. The questions we ask today, the theories we build, the observations we make, these are our contributions to the universe's ongoing story. A story that, for us, is still very much alive, vibrant and full of astonishing revelations. We are not merely observers of the cosmos, we are the cosmos observing itself, and there is no greater wonder than that. Thank you for joining me on this particular turn in our shared journey, for your patient attention and your willingness to delve into the deepest mysteries that bind us all. And so, we arrive at a precipice, a vantage point from which we have gazed across the vast unfolding narrative of our universe, from its searing genesis to its distant chilling demise. We have traced the faint echoes of the Big Bang, witnessed the birth of the first stars, and grappled with the invisible architects of cosmic structure, dark matter and dark energy. We have contemplated the probable end, the big freeze, a quiet fading into an endless night. It is a story both grand and intimate, a testament to the universe's relentless, patient evolution, and to our own remarkable capacity to observe, to question, and to understand. But even as we stand here, at the threshold of such profound understanding, we are acutely aware that our journey has only just begun. For every answer we uncover, a dozen new questions bloom, stretching the very fabric of our imagination. The universe, in its boundless generosity, offers us not only clarity, but also an ocean of unknowing, inviting us to dive deeper, to explore further. Consider again, if you will, the profound enigma of dark matter and dark energy. We have learned that they constitute an astonishing 95% of the cosmos, dictating its structure, its expansion, its very destiny. Yet we know them only by their gravitational whispers, their unseen hands shaping the visible world. Dark matter, that ethereal scaffolding, holds galaxies together, preventing them from spinning apart, an invisible gravitational anchor in the cosmic sea. Dark energy, that mysterious pervasive force, relentlessly pushes the universe apart, accelerating its expansion, driving it towards its ultimate solitary fate, What are they? This is the question that haunts the dreams of physicists and astronomers, that fuels countless experiments and observations across our world and beyond. We have theories, of course. For dark matter, perhaps it is a new, exotic particle, one that interacts so weakly with ordinary matter that it slips through our detectors, a ghostly presence in the quantum realm. We search for weakly interacting massive particles or WIMPs deep underground, shielded from cosmic noise, hoping to catch the faintest ripple of their passage. We build colossal observatories like the Large Hadron Collider, attempting to recreate the extreme conditions of the early universe, hoping to synthesize these elusive particles in a fleeting moment for dark energy. The mystery is even more profound, more unsettling. Is it a property of space itself, an inherent energy density that manifests as a repulsive force? Is it tied to the vacuum energy, the quantum fluctuations that constantly bubble up from nothingness? Or is it something far more exotic, a modification of gravity itself on cosmic scales, a fundamental misunderstanding of Einstein's elegant equations? Each possibility opens a new labyrinth of theoretical physics, each demanding new ways of seeing, new paradigms of thought. This profound ignorance, this vast expanse of the unknown, is not a source of despair, but rather of immense excitement. It is the frontier where the most exhilarating discoveries await. It is the universe's ongoing invitation to us, its conscious observers, to continue our relentless pursuit of knowledge. And how do we answer this call? How do we, with our relatively fragile instruments and our fleeting lifespans, hope to unravel such cosmic secrets? We do so with ingenuity, with collaboration, and with an unwavering sense of wonder. We build ever more sensitive telescopes, eyes that pierce through light years of cosmic dust and time itself. Imagine, if you will, the next generation of space observatories. Missions like the James Webb Space Telescope, already delivering breathtaking images, are just the beginning. The Nancy Grace Roman Space Telescope, Euclid, and the Vera C. Rubin Observatory are designed specifically to map the distribution of dark matter with unprecedented precision, to trace the subtle shifts in galaxy clusters, and to measure the universe's expansion history with exquisite detail. They are, in essence, our cosmic cartographers, charting the unseen currents and gravitational tides that shape the grand structure of everything. These instruments are not merely tools, they are extensions of our collective curiosity, designed to capture the faintest whispers from the dawn of time, to map the intricate web of dark matter that holds galaxies in their embrace, and to precisely measure the acceleration driven by dark energy. They allow us to look back, not just to the first stars, but to the subtle imprint left on the cosmic microwave background, seeking tiny anomalies that might hint at the nature of these dark constituents. Beyond the realm of light, we are also opening entirely new windows onto the cosmos. Gravitational wave astronomy, pioneered by observatories like LIGO and Virgo, offers us a new sense, a way to quote 10 the universe's most violent events: colliding black holes, merging neutron stars. While not directly detecting dark matter or dark energy, these gravitational ripples carry information from regions of extreme gravity, potentially revealing new physics or unexpected properties of spacetime that could, in turn, offer clues to the nature of the dark universe. Imagine a symphony of the cosmos, and we are just now beginning to tune into its bass notes, the deep rumblings that speak of immense power and fundamental interactions. And what lies beyond even these ambitious endeavours? What theoretical landscapes beckon to us when the observable universe itself begins to recede, when our understanding of fundamental particles reaches its limits? This is where the realms of philosophy and theoretical physics truly intertwine, where our models push the boundaries of what can be empirically tested, yet remain vital for guiding our future inquiries. One such fascinating, albeit speculative, concept that often emerges from these discussions is the idea of the multiverse. If our universe is just one among an infinite ensemble of universes, each with its own unique set of physical laws, constants and initial conditions, then perhaps the very fine-tuning of our own universe, the precise values of fundamental constants that allow for the formation of stars, planets, and ultimately conscious life, is not a cosmic accident or a divine intervention, but simply a statistical inevitability. In an infinite array of possibilities, there must be at least one where conditions are just right for us to exist and observe. This idea, while still firmly in the realm of theory and conjecture, offers a compelling, if humbling, perspective. It suggests that our universe, immense and awe-inspiring as it is, might be but a single bubble in a vast, frothing cosmic ocean, each bubble a universe unto itself. It is a concept that truly stretches the imagination, reminding us that the grand tapestry we have been unravelling might be but a single thread in an infinitely larger, more intricate design. We contemplate these ideas not to arrive at definitive answers, for many may forever remain beyond our grasp, but to expand our horizons, to challenge our assumptions, and to refine our understanding of what is possible. The universe, in its elegant complexity, constantly defies our preconceptions, urging us to think bigger, to question deeper. And in all of this, what remains constant is our intimate connection to this grand narrative. We are not mere spectators, we are participants. The very atoms that compose your body, the carbon in your cells, the iron in your blood, were forged in the hearts of ancient stars and scattered across the cosmos in their dying breaths. You are quite literally stardust made conscious, capable of contemplating the very processes that gave rise to your existence. This is the ultimate paradox, the profound beauty of our journey. We are tiny, ephemeral beings on a small planet orbiting an average star in an unremarkable galaxy. Yet our minds can encompass the entirety of space and time, from the quantum foam of the Big Bang to the chilling silence of the Big Freeze. We are the universe's way of knowing itself, its emergent consciousness, its collective memory. So, as we bring this particular segment of our Quote 12 to a gentle close, I invite you to carry this sense of wonder with you. Let the vastness of the cosmos not diminish your spirit, but rather expand it. Let the mysteries of dark matter and dark energy not discourage you, but ignite your curiosity. Let the knowledge of our cosmic origins and our ultimate fate serve as a reminder of the preciousness of this present moment, this fleeting opportunity to observe, to learn, and to connect. The journey of discovery is eternal, a patient, relentless blossoming of understanding. We have only just begun to read the first few pages of the universe's greatest story. And what an extraordinary privilege it is to be a part of it, to share in this quiet, thoughtful adventure, here in our dreamy academy. Thank you sincerely for joining me on this profound exploration. May your own contemplation of the cosmos continue to enrich your perspective, and may you always feel that deep, resonant connection to the grand, mysterious everything. Welcome back, dear friends, to this quiet corner of the cosmos, this dreamy academy where we allow our minds to stretch gently across the vastness of space and time. We have journeyed together through the universe's infancy, witnessed the genesis of its fundamental elements, and watched as the first stars ignited, scattering the seeds of complexity. We have grappled with the invisible architects of the cosmos, dark matter and dark energy, forces that shape galaxies and dictate the very cadence of expansion. We even dared to peer into the unimaginable future, contemplating the universe's eventual serene descent into the big freeze. But our journey, while extensive, is far from over. Indeed, the most thrilling chapters are still being written right now by countless brilliant minds across our planet. We stand at a precipice of understanding, looking out at a landscape of profound mysteries that beckon us forward. The universe, in its infinite wisdom, continues to withhold its deepest secrets, but it also provides us with the ingenuity and curiosity to relentlessly pursue them. Let us then turn our gaze from the grand sweep of cosmic history to the vibrant, active frontiers of discovery. Where do we search for the elusive dark matter? How do we hope to finally grasp the nature of dark energy? The quest is multifaceted, demanding both the patient observation of the heavens and the meticulous experimentation in laboratories buried deep beneath the earth. Consider dark matter, that unseen gravitational scaffolding that holds galaxies together, comprising roughly 27% of the universe's total mass energy content. We know its gravitational influence is profound, but its interaction with light and ordinary matter is virtually non-existent. This makes it incredibly difficult to detect, yet the pursuit is relentless, a testament to humanity's unyielding drive to understand. One primary approach involves direct detection experiments. Imagine vast shielded tanks, often filled with supercooled liquids like xenon or argon, buried deep underground in former mines. Here, away from the constant bombardment of cosmic rays, scientists hope to catch the faintest whisper of a dark matter particle colliding with an atomic nucleus. The theory is that if weakly interacting massive particles, or WIMPs, are indeed the constituents of dark matter, they should occasionally, ever so rarely, bump into ordinary matter. These experiments are designed to detect the minuscule recoil from such an impact. A fleeting flash of light or a tiny ionization signal. It is a search for a ghost, a whisper in the dark, demanding an almost unimaginable level of sensitivity and patience. We are listening for the faintest ripple in the cosmic pond, hoping it is the echo of dark matter passing through us, through our planet, through everything. Then there are indirect detection experiments. If dark matter particles can annihilate or decay, they might produce standard model particles, gamma rays, positrons, neutrinos, that we can detect. Telescopes like the Fermi Gamma Ray Space Telescope scan the skies for an excess of gamma rays originating from regions rich in dark matter, such as the galactic center or dwarf galaxies. Neutrino observatories like IceCube at the South Pole search for high-energy neutrinos that might be the telltale signature of dark matter interactions. We are looking for the afterglow of dark matter, the faint light left behind by its self-interactions. And finally, particle accelerators, like the Large Hadron Collider at CERN, offer a different avenue. Here, scientists smash particles together at incredible energies, recreating conditions akin to the early universe. The hope is that if dark matter particles exist and have a certain mass, they might be created in these collisions, appearing as missing energy or momentum in the detectors. It's like trying to find a specific piece of a puzzle by throwing all the existing pieces together with immense force, hoping the missing one will suddenly appear. Each of these approaches is a testament to our profound desire to touch the unseen, to give form to the invisible. But if dark matter is a ghost, dark energy is an even more profound enigma, a force that comprises nearly 68% of the universe and actively pushes the cosmos apart. Its discovery was a shock, a profound reorientation of our understanding of the universe's ultimate fate. Unlike dark matter, which clumps around galaxies, dark energy appears to be smoothly distributed throughout space, an intrinsic property of the vacuum itself. The leading candidate for dark energy is the cosmological constant, a concept first introduced by Einstein, then famously discarded and now resurrected with a vengeance. This constant represents the energy inherent in empty space, a constant pressure that drives expansion. However, theoretical calculations from quantum field theory predict a vacuum energy density that is many orders of magnitude larger than what we observe, a discrepancy so vast it's considered one of the greatest unsolved problems in physics. This cosmic embarrassment, this factor of 10 to the power of 120, whispers to us that our understanding of gravity, quantum mechanics, or both, is fundamentally incomplete. Perhaps dark energy is not constant at all. This leads to alternative theories such as quintessence, where dark energy is not a fixed property of space, but rather a dynamic evolving field, akin to the scalar fields that drove inflation in the early universe. If quintessence is real, its strength and influence might change over cosmic time, potentially altering the universe's ultimate destiny. This would mean that the future we glimpsed, the Big Freeze, might not be the only possibility, opening doors to even more exotic fates. To distinguish between these possibilities, astronomers continue to refine their observations of distant Type Ia supernovae, using them as cosmic standard candles to measure the universe's expansion history with ever-increasing precision. We also employ techniques like baryon acoustic oscillations, BAO, which are fossilized sound waves imprinted on the distribution of galaxies, acting as a cosmic ruler to map the expansion rate at different epochs. And weak gravitational lensing, the subtle distortion of light from distant galaxies by foreground matter, helps us map the distribution of both ordinary and dark matter, providing crucial clues about how dark energy influences the growth of cosmic structures. We are using the very light from the universe's past and the faint warping of space to chart the course of its future. Yet, our quest for understanding extends beyond these two dark titans. A new window into the universe has opened in recent years, a profound shift in how we perceive cosmic events, the detection of gravitational waves. These ripples in spacetime, predicted by Einstein over a century ago, are generated by the most cataclysmic events in the cosmos, the merging of black holes, the collision of neutron stars, perhaps even the echoes of the Big Bang itself. Observatories like LIGO and Virgo, and soon the space-based LISA mission, allow us to, quote, 14 the universe in a way we never could before. No longer are we solely reliant on electromagnetic radiation, light, radio waves, X-rays. Now, we can directly sense the warping and wobbling of spacetime itself. This offers an unparalleled opportunity to probe the universe's most violent phenomena, to test the limits of general relativity, and potentially to uncover new insights into dark matter and dark energy. Imagine if we could detect gravitational waves from the very early universe, before recombination, before light could travel freely. We would have an even more ancient baby picture of the cosmos, perhaps revealing the elusive physics of inflation or the true nature of quantum fluctuations. It is a new symphony of the cosmos, and we are just learning to listen. And what of the grandest theories, those that attempt to unify all forces, to explain the very fabric of existence? Concepts like string theory, which posits that fundamental particles are not point-like but tiny, vibrating strings, or the intriguing mind-bending notion of the multiverse. The multiverse, often arising from theories of eternal inflation, suggests that our universe is just one of an infinite number of bubble universes, each with its own physical laws and constants. While highly speculative and currently untestable, it offers a potential explanation for why our universe seems so perfectly tuned for life. Perhaps we reside in just one of countless cosmic possibilities, a fortunate happenstance in an infinite array. These are the frontiers of pure thought, where physics and philosophy intertwine, pushing the very boundaries of what we can conceive. My friends, we have travelled far, from the ultimate beginning to the distant future, from the smallest quantum fluctuation to the largest cosmic structures. We have touched upon the known and the unknown, the visible and the invisible. What remains after all this exploration is a profound sense of awe, a deep humility, and an unshakable connection. You, each of you, are an integral thread in this grand tapestry. The atoms that compose your body were forged in the heart of ancient stars, scattered across the cosmos in their fiery deaths, and eventually coalesced to form the planets, the life, and the consciousness that allows us to ponder these very questions. You are literally stardust, made conscious, capable of contemplating the very forces that created you. This is not merely a scientific fact, it is a poetic truth, a profound privilege. The universe's story is our story. Its mysteries are our mysteries. The journey of discovery is an eternal one, a relentless blossoming of understanding that will continue long after our individual lives have faded. We are merely custodians of this knowledge, passing the torch of curiosity from generation to generation. Thank you sincerely for joining me on this profound, slow and thoughtful adventure. Thank you for your patience, your curiosity, and your willingness to imagine the unimaginable. May your own personal journey through the cosmos continue, illuminated by the wonder of what we have explored together, and inspired by the vast, beautiful expanse of what still awaits discovery. Keep looking up, keep asking questions, and remember that you are an intimate, precious part of everything. Until next time, may your days be filled with cosmic wonder and quiet contemplation. Farewell. Welcome back, dear friends, to our quiet corner of the cosmos, to this shared space where we allow our minds to stretch and our imaginations to soar. We have journeyed together through the universe's fiery birth, witnessed the cosmic dawn, and watched, in our collective mind's eye, as the first stars ignited, scattering the seeds of heavier elements across the nascent void. We've seen galaxies coalesce, grand islands of stars, dust and gas, each a breathtaking city of light in the vast, expanding dark. And yet, as we gaze upon these magnificent structures, a profound realization begins to dawn, one that challenges our very perceptions of reality. For all the brilliance we have observed, all the light that reaches us from across billions of years, it represents only a fraction, a tantalizingly small sliver of what truly composes this universe we inhabit. What if, beneath the shimmering surface of the visible, there lies a hidden architecture, an invisible foundation that dictates the very dance of galaxies? This, my friends, brings us to the first of the great cosmic enigmas, a mystery that whispers to us from the very heart of galactic dynamics. Dark matter. For decades, astronomers meticulously observed the rotation of galaxies. They expected that stars further from a galaxy's centre, experiencing weaker gravitational pull, would orbit more slowly, much like planets further from our Sun. But what they found was startlingly different. Stars on the outer edges of galaxies were moving far too quickly, as if held in the grip of an unseen massive hand. The visible matter, the stars, gas and dust we can detect, simply isn't enough to generate the gravitational force required to keep these rapidly spinning galaxies from tearing themselves apart. Imagine a grand cosmic waltz. We see the dancers swirling and twirling, but their movements suggest an invisible partner, a silent, massive presence guiding their every step. This invisible partner, we now understand, is dark matter. It doesn't emit, absorb or reflect light, rendering it utterly transparent to our telescopes. We cannot see it, but we can feel its gravitational embrace. It is the gravitational scaffolding upon which the visible universe is built, forming vast, intricate cosmic webs and halos that cradle galaxies and clusters of galaxies. Without it, the structures we cherish, our own Milky Way included, would never have formed in the ways we observe them. So, what exactly is this elusive substance? The leading theory suggests it's composed of exotic particles, currently unknown to the standard model of particle physics, that interact only very weakly with ordinary matter, primarily through gravity. These hypothetical particles are often referred to as weakly interacting massive particles, or WIMPs. Scientists around the globe are engaged in a relentless, ingenious quest to detect them. Deep underground laboratories shielded from cosmic rays, host-sensitive detectors designed to register the faintest tremor of a WIMP colliding with an atomic nucleus. Particle accelerators, like the Large Hadron Collider, attempt to create these particles in high-energy collisions, hoping to catch a glimpse of their elusive signatures. Others search for indirect evidence, looking for gamma rays or neutrinos that might be produced when WIMPs annihilate with each other in dense cosmic regions. It is a testament to human curiosity and scientific tenacity, this patient pursuit of the invisible. Dark matter accounts for roughly 27% of the total mass energy content of the universe. Consider that for a moment. The ordinary matter that makes up stars, planets, and ourselves, everything we can see and touch, is a mere 5%. The vast majority of the universe's gravitational influence comes from something we cannot directly perceive. It is a humbling thought, isn't it? That the familiar is but a whisper in the grand cosmic symphony. But the universe in its boundless capacity for surprise, holds an even more profound secret, one that has utterly reshaped our understanding of its destiny. If dark matter is the hidden hand pulling galaxies together, then there is another, even more dominant force pushing everything apart. This brings us to the second, and perhaps greatest, enigma of modern cosmology: dark energy. For most of the 20th century, cosmologists believed that the universe's expansion, set in motion by the Big Bang, must be slowing down due to the collective gravitational pull of all matter within it. The big question was whether it would slow down enough to eventually reverse, leading to a big crunch, or if it would expand forever, albeit at an ever-decreasing rate. Then, in the late 1990s, two independent teams of astronomers observing distant Type I supernovae made a revolutionary discovery. These particular supernovae act as standard candles. They have a consistent peak luminosity, allowing astronomers to calculate their distance from us. By measuring their redshift, which tells us how quickly they are receding, and their apparent brightness, which indicates their distance, the teams expected to see a universe that was slowing its expansion. Instead, they found that these distant supernovae were fainter than expected, implying they were further away than they should have been if the expansion was slowing. The only logical conclusion was astonishing. The expansion of the universe is not slowing down, it is accelerating. Imagine throwing a ball into the air expecting it to slow down and eventually fall back to Earth, only to watch it inexplicably accelerate away into the sky, faster and faster. This is the cosmic equivalent of what those astronomers observed. Some pervasive, repulsive force is actively pushing space itself apart, overcoming the gravitational attraction of all matter and dark matter. This mysterious force, responsible for the accelerating expansion, is what we call dark energy. Dark energy is not localized like dark matter. It is thought to be an intrinsic property of space itself, a constant energy density that permeates the entire cosmos. As space expands, more space is created, and with it, more dark energy. It is the dominant component of our universe, accounting for approximately 68% of its total mass energy. Think of that. 95% of the universe is made of stuff we cannot see, cannot touch, and barely understand. What is its fundamental nature? This is the greatest unsolved mystery in cosmology. The simplest explanation is that dark energy is the cosmological constant, a concept first introduced by Einstein, but later abandoned. It would represent the energy of the vacuum of space, an inherent pressure that pushes space apart. However, theoretical calculations for the vacuum energy predict a value that is astronomically larger, by a factor of 10 to the power of 120, a 1 followed by 120 zeros, than what we observe. This staggering discrepancy is one of the most significant problems in all of physics. Is it a cosmological constant, or is it a dynamic field, perhaps something called quintessence, that changes over time? The answers remain elusive, a profound challenge to our understanding of the fundamental laws of nature. To unravel the secrets of dark energy, astronomers employ a variety of techniques, studying more distant supernovae, mapping the large-scale distribution of galaxies through baryon acoustic oscillations, fossilized sound waves from the early universe, and analyzing the subtle distortions of light from distant galaxies caused by weak gravitational lensing. Each method offers a different window into this enigmatic force, helping us to piece together the cosmic puzzle. As we grapple with these immense mysteries, the universe continues to reveal itself in new and unexpected ways. For centuries, our primary senses for exploring the cosmos were sight, through telescopes, and more recently radio waves. But a new era of cosmic exploration has dawned, allowing us to perceive the universe not just with our eyes, but with our ears, so to speak. This brings us to the frontier of gravitational waves. Predicted by Albert Einstein's theory of general relativity over a century ago, gravitational waves are ripples in the very fabric of spacetime, generated by the most violent and energetic events in the universe. Imagine spacetime as a vast, taut trampoline. When massive objects accelerate and collide like two colossal black holes spiraling into each other, they create disturbances, waves that propagate outward at the speed of light, stretching and squeezing space as they pass. For a long time, these waves were purely theoretical, considered too faint to ever detect. But in 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, a monumental scientific endeavour, made history by directly detecting gravitational waves for the very first time. The signal was unmistakable, the faint fleeting chirp of two black holes, each dozens of times more massive than our Sun, merging billions of light years away. This was more than just a confirmation of Einstein's theory. It opened an entirely new window onto the universe. We can now hear the universe's most extreme phenomena, the cataclysmic collisions of black holes, the violent mergers of neutron stars, which we now know are factories for heavy elements like gold and platinum, and perhaps, in the future, even whispers from the very first moments of the Big Bang itself. Gravitational wave astronomy promises unprecedented insights into the nature of space-time, the life cycles of massive stars, and the fundamental laws governing our cosmos. With dark energy dominating the universe's destiny, the ultimate fate of our cosmos appears to be largely sealed. The accelerating expansion driven by dark energy strongly favours a scenario known as the Big Freeze, or heat death. This is not a sudden dramatic end, but a slow, inexorable fading into infinite cold and darkness. As the eons pass, the accelerating expansion will push galaxies further and further apart, eventually beyond each other's cosmic horizons. What we now see as a universe teeming with billions of galaxies will, in the unimaginably distant future, appear as an empty, lonely void, with only our own local group of galaxies remaining gravitationally bound. Stars having exhausted their nuclear fuel will die out, and no new ones will form as the raw materials for star formation become too dispersed and cold. Black holes will slowly evaporate over truly astronomical timescales through Hawking radiation. Eventually, even the fundamental particles will drift apart, isolated and alone, in a universe of ever-increasing entropy, where no energy differences remain to power any process. It is a future of ultimate stillness, an infinite expanse of cold, dark emptiness. It is a sobering thought, perhaps, but also a testament to the scale of cosmic time and the grandeur of the processes at play. Other fates, like the E's quote 23, where gravity eventually wins and the universe collapses back on itself, or the quote 24, where dark energy becomes so powerful it tears apart atoms themselves, are now considered less likely given current observations. The Big Freeze stands as the most probable conclusion to our universe's grand narrative. And yet, even with these profound insights and unsettling predictions, the human mind continues to push the boundaries of knowledge, venturing into realms that currently lie beyond direct observation. This is where the truly speculative, yet deeply compelling theories of modern cosmology come into play. Consider for a moment the remarkable fine-tuning of our universe. The fundamental physical constants, the strength of gravity, the electromagnetic force, the masses of elementary particles, seem exquisitely calibrated for the emergence of complex structures, stars, and ultimately life itself. If these constants were even slightly different, the universe as we know it would not exist. Is this mere coincidence? Or is there a deeper explanation? One profound idea that attempts to address this is the concept of the multiverse. The multiverse hypothesis suggests that our universe is not the only one, but rather one of an infinite number of universes, each with its own unique set of physical laws and constants. In this grand cosmic ensemble, it becomes statistically inevitable that at least one universe would have the precise conditions necessary for life to arise. It's like imagining an infinite number of lottery tickets. Eventually, one of them is bound to be a winner. Different theoretical frameworks, such as eternal inflation or string theory, offer mechanisms for the generation of such a multiverse. And speaking of string theory, this highly theoretical framework proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating one-dimensional strings. The different vibrational modes of these strings correspond to different particles and forces, offering a potential path towards a unified, quote, 25, quote, that reconciles general relativity with quantum mechanics. While still largely unproven and highly mathematical, string theory, and its extensions like M-theory, continue to inspire and challenge physicists in their quest for the ultimate nature of reality. These are the frontiers, dear friends, where science meets philosophy, where our instruments reach their limits, and our minds take flight into the realm of the truly unknown. Dark matter, dark energy, gravitational waves, the ultimate fate of the cosmos, and the tantalizing possibility of a multiverse. These are the active, thrilling, and humbling puzzles that define modern cosmology. They remind us that the story of the universe is still being written, and we, with our insatiable curiosity and relentless pursuit of understanding, are privileged witnesses and participants in this ongoing, magnificent unfolding. We have traversed the vastness of cosmic history, from the initial spark to the distant future, and yet, the greatest adventure often lies in the questions that remain unanswered. Thank you, as always, for joining me on this journey into the profound. We have together traced the universe's grand narrative, from the incandescent flash of its birth to the chilling prospect of its distant future. We have peered into the heart of stars, felt the gravitational embrace of unseen matter, and pondered the accelerating push of an enigmatic energy. We have listened for the whispers of gravitational waves, those ripples in spacetime, beginning to offer us a new symphony of cosmic events, and we have touched upon the profound, almost dizzying concepts of the multiverse and the elegant yet elusive promise of string theory. Yet, as we stand at this precipice of understanding, gazing out at the vast, shimmering sea of the unknown, it becomes ever clearer that for every answer we uncover, several new, even more profound questions emerge. This perhaps is the true essence of our cosmic journey, an eternal dance between discovery and mystery, between illumination and the deep, rich darkness that still holds so many secrets. Let us linger a moment longer within these realms where the known meets the imagined, where the measurable intertwines with the profoundly theoretical. The detection of gravitational waves, as we briefly explored, was not merely a scientific triumph. It was the opening of an entirely new sense, an auditory window into a universe that had, until now, communicated primarily through light. Imagine, if you will, being able to hear the universe breathe, to feel its most violent upheavals directly. This new frontier promises to revolutionize our understanding of black holes, not just as static objects, but as dynamic entities that merge, spin, and ring down, sending shivers through the very fabric of existence. We are beginning to map the dark gravitational universe, seeing phenomena that emit no light, witnessing the unseen forces at play in ways previously unimaginable. This is just the beginning, a nascent era where observatories across the globe and eventually in space will form a vast network, listening to the echoes of creation, the violent dance of neutron stars, and perhaps, one day, even the faint, primordial gravitational waves from the Big Bang itself, a direct whisper from the universe's infancy, unhindered by the opaque fog that veiled the early cosmos from light. From the palpable reality of gravitational waves, we venture now into territories that stretch the very fabric of imagination, realms born from the deepest theoretical urgings of physics. Consider the multiverse. The idea, at first glance, feels almost fantastical, plucked from the pages of science fiction. Yet, within the rigorous frameworks of modern cosmology and quantum mechanics, it arises as a compelling, even elegant solution to some of the universe's most perplexing puzzles. One such puzzle, perhaps the most profound, is the apparent fine-tuning of our universe. Why are the fundamental constants of nature, the strength of gravity, the mass of an electron, the precise value of dark energy, calibrated with such astonishing precision? If these values were even slightly different, the universe as we know it, with its stars, galaxies, and life, could not exist. It's akin to finding yourself in a casino, rolling a dice 1,000,000,000,000 times and having it land on the same improbable number every single time. It begs the question, is it an incredibly improbable coincidence, or is there a deeper explanation? The multiverse offers a potential answer. Perhaps our universe is not the only one. Imagine an infinite ensemble of universes, each born with slightly different physical laws, different constants, different initial conditions. In such a vast cosmic landscape, it becomes statistically inevitable that at least one universe would possess precisely the right conditions for stars to ignite, for elements to forge, and for life to eventually emerge. Our existence, in this view, is not a miracle but a selection effect. We find ourselves in this universe because it is the only kind of universe where observers like us could arise. This concept branches into several fascinating interpretations. There are theories suggesting an infinite series of quote 28 quote, constantly bubbling out of an eternally inflating superregion, each a distinct cosmic bubble. Others propose that every quantum measurement in our universe causes it to split into myriad parallel realities, each representing a different outcome, and still others suggest that the very dimensions of spacetime could be different in other "29" or membranes floating in a higher dimensional bulk. While these ideas remain deeply speculative, they represent humanity's relentless pursuit of fundamental explanations, pushing the boundaries of what we conceive as reality itself. They ask us to consider not just our universe, but the possibility of a cosmos far vaster and stranger than we ever dared to imagine. And then there is string theory, or more broadly M theory, which seeks to unify all the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, into a single, elegant framework. For decades, physicists have struggled to reconcile Einstein's general relativity, which describes gravity on cosmic scales, with quantum mechanics, which governs the subatomic world. They are two profoundly successful theories, yet they speak different languages, especially when attempting to describe extreme environments like the singularity of a black hole or the very first moments of the Big Bang. String theory proposes a radical solution. Perhaps the fundamental constituents of reality are not point-like particles, but tiny, vibrating one-dimensional strings. Imagine these strings as infinitely thin rubber bands, each vibrating at different frequencies. Just as different vibrational modes on a guitar string produce different musical notes, different vibrational patterns of these fundamental strings are hypothesized to give rise to all the various particles we observe: electrons, quarks, photons, and even the graviton, the hypothetical quantum of gravity. This theory's mathematical elegance is breathtaking. It naturally incorporates gravity and requires the existence of extraspatial dimensions beyond the three we perceive and the one dimension of time. These extra dimensions, according to the theory, are not missing, but are curled up, compactified into incredibly tiny spaces, too small for us to detect directly. Imagine an ant walking on a garden hose. From a distance, it appears to be moving in one dimension, along the length of the hose. But up close, the ant can also move around the circumference of the hose, revealing a second curled-up dimension. Similarly, these extra dimensions could be present everywhere, shaping the very fabric of our reality in ways we are only beginning to comprehend. String theory offers a potential theory of everything, a unified description of the cosmos at its most fundamental level. It attempts to answer not just what the universe is made of, but how. It all fits together, from the smallest quantum fluctuations to the grandest cosmic structures. However, it remains a theoretical construct, a magnificent mathematical edifice awaiting experimental verification. The energies required to probe these tiny strings or extra dimensions are far beyond anything our current particle accelerators can achieve. Yet, the search continues, driven by the profound beauty and consistency of the theory itself, and by the tantalizing promise of a complete understanding. These frontiers, gravitational waves as a new observational window, the multiverse as a grander context for our existence, and string theory as a unified description of reality, are not merely academic pursuits. They represent the continuing evolution of human consciousness, our collective endeavor to understand the universe from which we arose. They are our way of pushing against the boundaries of ignorance, illuminating the darkness with the light of inquiry. Think for a moment about the journey we have undertaken, from the initial quantum fluctuations to the formation of stars, galaxies, and the very elements that comprise us. We are quite literally stardust made conscious, capable of turning our gaze outward, back towards our origins, and inward to the very nature of our awareness. This capacity for self-reflection, for asking why and how, is perhaps the most extraordinary phenomenon in the universe. The pursuit of cosmology, then, is not just about measuring distances or calculating expansion rates. It is a deeply philosophical and profoundly human endeavour. It is about understanding our place, our significance, and our ultimate fate within this vast, dynamic, and ever-unfolding cosmos. It is about embracing the humility that comes with realizing how much we do not know, while simultaneously celebrating the astounding knowledge we have managed to gather. As we continue to build ever more sensitive instruments, to devise ever more elegant theories, we are not just accumulating facts, we are expanding the very boundaries of human thought. We are learning to speak the language of the cosmos, to decipher its ancient messages, and to perhaps one day understand the full scope of its magnificent story. The universe, in its relentless unfolding, continues to present us with new challenges and new wonders. Dark matter remains unseen, its identity a profound mystery. Dark energy continues its accelerating push, its nature a riddle wrapped in an enigma. And at the edges of our theoretical understanding, new concepts like the holographic principle suggest that the information content of a region of space might be encoded on its boundary, hinting at an even deeper, more fundamental reality. Could our three-dimensional universe be a projection of information from a two-dimensional surface? These are the questions that fuel the minds of scientists today, pushing them into realms that blur the lines between physics, mathematics, and philosophy. This journey of discovery is patient, relentless, and endlessly rewarding. It is a testament to the enduring human spirit of curiosity, the innate drive to comprehend the world around us. And in this shared exploration, we are all participants, connected not just by our common humanity, but by our intimate cosmic heritage. We are not mere observers of this grand tapestry. We are integral threads within it, woven into the very fabric of space-time, our consciousness a fleeting yet profound manifestation of the universe's own capacity for self-awareness. Thank you sincerely for joining me on this particular leg of our cosmic voyage. Your presence, your thoughtful engagement, and your willingness to contemplate these profound mysteries truly enrich this shared experience. We have traversed billions of years and unimaginable distances, all from the comfort of our shared intellectual space. But the journey, dear friends, is far from over. The universe continues its grand, silent expansion, and with it, our understanding continues to grow patiently, relentlessly. We have only just begun to listen to its deepest secrets, having ventured into the profound theoretical realms where the very fabric of reality might be woven from vibrating strings, or where our universe is but one shimmering bubble in an infinite cosmic foam. We find ourselves standing at a fascinating precipice. We've stretched the boundaries of what we can imagine, invited the most audacious hypotheses into our quiet contemplation, and now we gently draw back not from the wonder, but to ground ourselves once more in the astonishing dance between what we know with growing certainty and the vast luminous ocean of what remains a beautiful, beckoning mystery. This journey, you see, is not a race to a final answer, but a patient, relentless blossoming of understanding. It is a testament to the enduring human spirit, a reflection of our innate drive to gaze upwards and ask. Quote 35 and quote 36. Let us for a moment trace our steps back through the grand narrative we've been unfolding, but this time with an eye not just for the milestones of discovery, but for the profound questions that linger, like faint echoes from an origin we are still striving to comprehend. We began with the Big Bang, that singular momentous genesis, approximately 13.8 billion years ago. We spoke of it not as an explosion into space, but as the sudden rapid expansion of space itself. We described the initial almost unimaginably hot and dense state, a crucible of pure energy. But even here, at the very inception, questions bloom. What preceded this moment, if anything? What truly triggered this expansion? Can we ever glimpse the physics of that Planck epoch, that fleeting instant before our current laws truly took hold, when space-time itself might have been a frothing quantum foam? These are whispers from an origin, inviting us to delve deeper into the very nature of time and existence. Then came the era of cosmic inflation, a spectacular exponential growth that smoothed out the universe to an astonishing degree, laying the groundwork for the large-scale structure we observe today. It ironed out wrinkles, flattened the cosmic canvas, yet simultaneously stretched tiny quantum fluctuations into macroscopic seeds for future galaxies. Inflation elegantly solves several puzzles, offering a compelling explanation for the universe's uniformity and flatness. But what drove inflation? What was the inflaton field, this mysterious energy that powered such a colossal expansion, and why did it eventually cease? We have the what and the how in broad strokes, but the why and the how, or what force, behind this cosmic engine remains a subject of intense theoretical exploration. As the universe cooled, the stage was set for Big Bang nucleosynthesis, the forging of the lightest elements, hydrogen and helium in a cosmic oven. This period, lasting only a few minutes, left an indelible chemical signature that perfectly matches our observations of the universe's pristine early composition. It's a triumph of our models. Yet even this foundational chapter holds secrets. Precision measurements of primordial light element abundances continue to refine our understanding, sometimes hinting at subtle discrepancies that might point to new particles or forces beyond our current standard model. The universe, in its quiet elegance, is always offering new clues. And then the universe became transparent. After 380,000 years, electrons finally settled into stable orbits around atomic nuclei, releasing the ancient light we now observe as the cosmic microwave background. This gentle hum, these faint temperature variations across the sky, are a snapshot of the infant universe, a baby picture revealing the subtle ripples that would grow into galaxies and clusters. The CMB is our most powerful tool for understanding the early cosmos. Yet, its patterns, while incredibly informative, still hold secrets. Anomalies, like the quote 37 or certain large-scale alignments, occasionally pique our curiosity, challenging us to ask if there are deeper, more subtle influences at play, perhaps from pre-inflationary physics, or even interactions with other universes in a multiverse scenario. The static on this ancient radio, though largely understood, still occasionally crackles with tantalizing hints of the profoundly unknown. Gravity, that tireless architect, then began its patient work, amplifying these tiny fluctuations, drawing together the diffuse gas into the first luminous stars. These stellar pioneers, massive and short-lived, ignited the universe, forged the first heavy elements, and then, in spectacular supernova, enriched the cosmos with the building blocks of planets and life. This is the alchemy of creation, the cosmic cycle of birth, death, and rebirth that led to galaxies, to our solar system, to you and me. But the exact timing and nature of these quote 38 quote and quote 39 quote, the epoch of reionization, is still being meticulously pieced together by telescopes like the James Webb Space Telescope. How did these earlier structures form and evolve in a universe still largely devoid of heavy elements? What role did dark matter play in shaping these very first cosmic cities? And speaking of dark matter and dark energy, we arrive at the profound, persistent mysteries that comprise 95% of our universe. Dark matter, this invisible gravitational scaffolding, holds galaxies together, shaping the cosmic web. We infer its presence through its gravitational pull, observing its undeniable effects on galactic rotation and light bending. But its true identity remains elusive. Is it a new type of particle, perhaps WIMPs, or axions, or something else entirely? Our detectors, buried deep underground or smashing particles together in colossal accelerators, are diligently searching. But the universe keeps its secrets close. It is a quiet, transparent presence, yet its influence is paramount. And then, the most perplexing enigma of all, dark energy. This mysterious repulsive force, accelerating the expansion of our universe, pushing galaxies apart at an ever-increasing rate. It dictates the ultimate fate of the cosmos, leading us towards a big freeze. We discovered it through the subtle dimming of distant supernovae, a cosmic speedometer revealing the universe is hitting the gas, not the brakes. But what is it? Is it Einstein's cosmological constant, the inherent energy of empty space, a vacuum that is anything but empty? If so, why is its observed value so astronomically smaller than theoretical predictions, a discrepancy so vast it's been called the quote 40? Or is it a dynamic, evolving field quintessence, constantly shifting its influence? Dark energy is the universe's ultimate riddle, a challenge that pushes our understanding of fundamental physics to its very limits. It is the greatest unknown, stretching the very fabric of our imagination. So, you see, our grand cosmic story, while filled with incredible triumphs of human intellect, is also a symphony of unanswered questions. Each discovery, each illuminated path, often reveals a new, even more profound unknown stretching out before us. This is the very heart of scientific inquiry, a beautiful, unending conversation with the universe. We do not pretend to hold all the answers. Indeed, the very strength of our scientific endeavour lies in its humility, its willingness to admit quote 41, and then to relentlessly pursue the next piece of the puzzle. Science is not a dogma. It is a dynamic, evolving process. It is a constant cycle of observation, hypothesis, experiment, and refinement. We build models, test them against the universe's unfiltered truth, and when they fall short, we do not despair, but rather, we rejoice. For a model that fails is not a failure of understanding, but an invitation to a deeper one, a signpost pointing towards new physics, new insights, new ways of seeing the unseen. This is why we invest so much in colossal telescopes that peer back in time, in sensitive detectors that listen for the faint whispers of dark matter, in observatories that feel the ripples of gravitational waves, and in accelerators that recreate the conditions of the early universe. These instruments are our extended senses, amplifying our ability to interact with the cosmos, to gather more clues in this greatest of detective stories. They are our way of asking the universe more precise, more penetrating questions. And through it all, it is eus. It is you and E and all of humanity that are the consciousness of this cosmic endeavour. We are the universe's way of reflecting upon itself, of seeking to understand its own magnificent origins and destiny. Our curiosity is not separate from the cosmos. It is an integral part of its ongoing story. We are not mere observers on the sidelines. We are active participants, woven into the grand tapestry of everything. Every question we ask, every theory we formulate, every observation we make, adds another thread to this intricate, evolving masterpiece. As we look towards the future of cosmology, we see not an end to discovery, but an acceleration of it. Next-generation telescopes promise to show us the universe in unprecedented detail, perhaps even unveiling the first stars themselves. New gravitational wave observatories, both on Earth and in space, will open entirely new windows onto cosmic phenomena, allowing us to quote 42, the universe's most extreme events, and perhaps even the very echoes of the Big Bang itself. Experiments will continue to probe the nature of dark matter and dark energy, pushing the boundaries of particle physics and gravity. And theoretically, we will continue to grapple with the grand unification, seeking a single, elegant framework that can describe all forces and particles, perhaps even bridging the chasm between quantum mechanics and general relativity. The journey continues, endlessly fascinating, endlessly humbling. We embrace the vastness of the unknown, not with fear, but with a profound sense of awe and anticipation. For it is in these unexplored territories, these luminous mysteries, that the greatest discoveries often lie waiting, and it is our shared human curiosity that will continue to light the way. We stand now at a luminous threshold, having journeyed together through the grand narrative of our universe, a story told not just in equations and observations, but in the very fabric of existence. We began with the profound singularity of the Big Bang, a moment not of explosion into space, but of the quiet, relentless blossoming of space itself, carrying with it the seeds of everything that would ever be. Remember the inflationary epoch, that fleeting, unimaginably rapid expansion that smoothed the cosmos and stretched quantum whispers into the macroscopic blueprints of galaxies. We felt, perhaps, the immense heat of nucleosynthesis, the forging of the universe's lightest elements, the foundational building blocks of stars and planets, and indeed of us. We then navigated the cosmic dark ages, a vast silent expanse before the first stars ignited, a period of profound opacity that gave way, some 380,000 years after the beginning, to the release of the cosmic microwave background. Do you still feel the echo of that ancient light, bathing the universe even now, a testament to its earliest, most uniform state? It is a whisper from an origin, an intimate portrait of infancy that continues to guide our understanding. From these simple beginnings we watched gravity, that patient, relentless sculptor, gather matter into the first colossal population 3 stars, these magnificent short-lived giants, burning with an intensity we can only imagine, were the universe's first alchemists, forging heavier elements in their stellar cores. Their spectacular deaths, supernovae explosions that ripped through nascent space, scattered these precious elements, carbon, oxygen, nitrogen, iron, the very ingredients for life, into the cosmic dust. It was an act of profound creation through destruction, enriching the interstellar medium, allowing the formation of second and third generation stars, and eventually the intricate swirling galaxies we observe today. Our journey then led us into the profound enigmas that challenge our current understanding. We grappled with the invisible embrace of dark matter, that mysterious scaffolding comprising some 27% of the universe, whose gravitational pull shepherds galaxies and structures on the grandest scales, yet refuses to interact with light or any known force save gravity itself. Its true nature remains a tantalizing mystery, a silent partner in the cosmic dance, beckoning us toward new physics beyond our standard model. Imagine the profound implications if we could truly unravel its identity, if we could directly detect these elusive particles that permeate our very being, yet remain utterly hidden. And then, the greatest surprise of all, dark energy. The universe is not merely expanding, it is accelerating its expansion, driven by this enigmatic force that accounts for approximately 68% of its total energy density. This discovery, barely a quarter-century old, redefined our cosmic destiny, pointing towards a future of increasing isolation and eventual heat death. The vast, chilling emptiness that awaits as galaxies recede beyond our observable horizon, as stars exhaust their fuel and all thermodynamic activity grinds to a halt. The quote 43 is not a sudden dramatic event, but a slow, inexorable fading, a gentle whisper into eternal night. The nature of dark energy, the immense discrepancy between theoretical predictions and observed values, stands as the most profound, humbling challenge in modern cosmology. It is a cosmic question mark, stretching the very fabric of imagination. We touched upon the new frontiers of discovery, the revolutionary insights offered by gravitational waves, those ripples in spacetime that allow us to quote 44, the universe's most violent events, the mergers of black holes, the collisions of neutron stars. This new sense, this new window, promises to unveil phenomena previously hidden, providing an entirely fresh perspective on the cosmos. We also briefly peered into the speculative realms of the multiverse, where our universe might be but one in an infinite ensemble, and string theory, which attempts to unify all forces into a symphony of vibrating strings. These are not yet proven theories, but they represent humanity's relentless pursuit of a deeper, more elegant truth, a comprehensive understanding that transcends our current boundaries. So, here we are, having traversed billions of years and unimaginable distances, having explored the known and the unknown, the seen and the unseen. But why? Why this patient, relentless quest for understanding? What compels us to decipher these cosmic hieroglyphs, to trace the lineage of starlight back to its primordial origins? Perhaps it is because, in a profound and undeniable way, this story is our story. We are not merely observers gazing upon a distant spectacle. We are integral threads in this grand tapestry. The carbon in your bones, the oxygen in your breath, the iron in your blood, these are not terrestrial elements. They are cosmic dust, forged in the hearts of ancient stars scattered across the void, and eventually gathered into the raw materials that formed our planet and ultimately us. We are quite literally stardust made conscious, the universe contemplating itself. This realization fosters an intimate connection, a sense of belonging to something immeasurably vast and ancient, yet profoundly personal. Our very existence is a testament to the universe's capacity for complexity, for self-organization, for wonder. To understand the cosmos is, in a very real sense, to understand ourselves. It is to place our brief, precious lives within a context that stretches beyond comprehension, yet simultaneously grounds us in the here and now. The journey of cosmological discovery is far from over. Indeed, in many ways, it feels as though we are just beginning to truly listen, to truly see. The next decades promise an explosion of new data, new instruments, and new insights that will push the boundaries of our knowledge even further. Consider the James Webb Space Telescope, JWS, for instance, already delivering breathtaking images and data. This marvel of engineering is peering back in time, observing the very first galaxies as they formed, shedding light on the cosmic dawn and the reionization epoch. It is revealing the atmospheres of exoplanets with unprecedented detail, bringing us closer to answering the profound question, are we alone? JWST is not just a telescope, it is a time machine, allowing us to witness the universe in its infancy, to understand the conditions under which stars and galaxies first emerged from the primordial darkness. Beyond JWST, the scientific community is planning the next generation of observatories, upcoming ground-based telescopes with immense mirrors, like the extremely large telescope ELT and the Giant Magellan Telescope GMT, will offer unparalleled resolution and light-gathering power, allowing us to study distant galaxies, stellar populations, and the faint signals from the early universe with even greater precision. In the realm of gravitational waves, the future is equally exciting. While LIGO and Virgo have opened this new window from Earth, the proposed Laser Interferometer, Space Antenna, LISA, mission promises to detect gravitational waves from entirely different sources. The mergers of supermassive black holes at the centers of galaxies, the echoes of the very early universe, and potentially even more exotic phenomena. Imagine detecting ripples from the inflationary epoch itself, a direct probe of the universe's ultimate beginning. The quest for dark matter continues with an array of sophisticated experiments deep underground and at particle accelerators. Scientists are building increasingly sensitive detectors, hoping to catch the faint signal of a weakly interacting massive particle, WIMP, or other hypothesized dark matter candidates. Concurrently, new astronomical surveys like the Vera C. Rubin Observatory will map billions of galaxies, providing unprecedented detail on the distribution of dark matter and its influence on cosmic structure. And dark energy, that most elusive of cosmic components, remains a prime target for research. Future large-scale surveys, such as the Euclid mission and the Dark Energy Spectroscopic Instrument, DIESL, are meticulously mapping the universe's expansion history with incredible precision, seeking subtle clues that might distinguish between a cosmological constant and a more dynamic, evolving dark energy field. Each new data point, each new observation, brings us a step closer to understanding this ultimate driver of our universe's fate. These endeavours are not merely scientific projects, they are collective acts of curiosity, expressions of humanity's innate drive to explore and understand. They are testaments to our shared intellectual heritage, built upon centuries of observation, theory, and relentless questioning. As we conclude this particular chapter of our cosmological journey, I invite you to carry these ideas with you. Let the vastness and the wonder of the cosmos resonate within you. Let the knowledge that you are made of stardust, that you are a conscious part of this unfolding epic, inspire a deeper sense of connection and purpose. The universe is not just out there, it is within us, and we are within it. Thank you for joining me on this slow and thoughtful adventure. Thank you for your patience, your curiosity, and your willingness to contemplate the grandest story ever told. It has been a true privilege to share this space, this time, and these profound ideas with you. May your own journey of discovery, both inward and outward, continue to unfold with wonder and revelation.